We've learned that energy can be stored in 5 different ways in systems. We've also learned that energy can be transferred in 3 different ways. We have a couple of models for energy storage and transfer. One that works good for closed systems, tracking how energy is stored in a closed system, is the pie chart model. We also found that we can use an energy bar graph and system diagram that works really well for all kinds of systems, including open systems where energy can be transferred into or out of the system across the boundary. These graphical models, like pie charts and energy bar and system diagrams, are great ways of getting our head wrapped around the idea of energy storage and transfer, but working chemists and physicists and engineers would like something that doesn't involve having to draw a lot of graphs. They'd like something that's a little bit more like shorthand. So in this video, we're going to explore using symbols to represent energy storage and transfer. So this presentation is about symbolic representations of energy storage and transfer. So rather than graphical representations, we're going to just use symbols to kind of stand for the same thing that we would see in energy bar and system diagram. By the way, energy bar and system diagrams, sometimes students nickname these things LOL charts, and if you think about what they look like, it's not hard to see why they're called that, because you have the bar graph, and then you have the system diagram in the middle, which is a circle, and a bar graph on the right. And without the bars in place, the bar graphs just look like L's, and the system circle looks like an O, obviously, so LOL is a kind of a shorthand that we use when we're talking about energy bar, graph, and system diagrams. Let's take a look at this energy bar and system diagram and try and come up with a way that we could use symbols to model it. At first, we can see that there's a little bit of elastic energy stored. Some energy enters the system through working, so afterwards, in the final L of the LOL chart, there's more energy stored. A lot more elastic energy and some gravitational energy. One way that we could represent this with symbols is, but we could say that the energy at A, let's call A the start and B the end, the energy at A is less than the energy at B. That's not false, it's true. So it's good. But we could do better. Another thing that we could do is, by using E elastic at A less than E gravitational at B plus E elastic at B, is we could give a little more detail. Not only do we now know that the energy at B is greater than the energy at A, we now know what storage modes are used. So that's also built into our symbols. This one's even better, because it doesn't only tell us what energy storage modes are used at A and B, but it also tells us the energy transfer mechanism that got the energy into the system. So we're starting out with the energy storage. We got E elastic at A, so that's modeled by this symbol, plus working. And we're using plus here because energy is added to the system. And the starting energy, the elastic energy at A, plus the working energy is the total energy at B, which is the EG that is stored and the E elastic that is stored. So this just uses symbols to stand in for the chart. Let's try this one. Just stop the video and see if you can draw a good symbolic representation for this energy storage and transfer. Okay, on the left-hand side, we see 2 energy storage modes, chemical and thermal. So we could write down E chem at A plus E therm at A as our starting point. Then we lose energy here through heating. The arrow is going out of the circle. So we're going to take away energy from the beginning amount, and that equals the ending amount of energy, which is stored in 2 modes. Again, it's chemical and thermal. So now we'll say E chem at B plus E therm at B. Now I'm just using A and B because I'm calling the starting snapshot A and the ending snapshot B. But you could use I and F for initial and final, or S and F for start and final. That wouldn't matter. The key is, when you put together this symbolic representation, somebody who understands an LOL chart should be able to read your diagram and in their mind get a good feel for how the energy is being stored, how the energy is being transferred, and be able to recreate this chart if they wanted to. Here's another one. Stop the video, write a symbolic representation, and then check in. See if you got it right. Okay, so the left-hand side, there are 2 energy storage modes. It's chem and therm again. So E chem at A plus E therm at A is our starting point. Now we're losing energy through heating, so minus Q. But we're gaining some energy through radiation, so plus R. So the start minus the loss plus the gain is the end, which is E-chem at B plus E-therm at B, because those are the two storage modes that we see on the ending. So now we've taken a look at symbolic representations that can take the place of graphical representations. Sometimes it's a little harder to visualize if you're looking at a symbolic representation, but it's way easier to write. And in a later class, you may be quantifying like how much chemical energy, how much thermal energy, how much heating, how much radiation, how much working is done. And when that's the case, it's way easier to do algebra with an equation than it is with a graphical representation. So that's a useful shorthand once you start to understand the ideas of energy storage and transfer.